Hey, so I'm Naveen, and today I'm going to be talking about fee market design beyond the model. This is joint work with Mariam Barani at Ritual, and Ritual is an infrastructure startup that's trying to bring AI operations on chain. So demand for trusted computation that's supported by decentralized blockchains has grown increasingly heterogeneous over time. We started with simple financial transfers. This became general Turing complete smart contracts. And now these contracts have heterogeneous demands over storage and compute. And today, infrastructure startups, including Ritual, are foreseeing yet more heterogeneous demand for resource-intensive operations. And in tandem with this change, supply has also become more heterogeneous. Early Bitcoin could basically just support these financial transfers. Now blockchains support these arbitrary general smart contracts. And with blobs and dank sharding, we now have support for these heterogeneous storage and compute demands. And now there's also a whole suite of entities, off-chain entities, that are trying to provide support for these resource-intensive operations as well. So in accordance with these trends, the market design problem of matching demand to supply has also gotten more complex. In early Bitcoin, where all the transactions were simple financial transfers, they were essentially computationally indistinguishable from each other. And so the problem of block inclusion was essentially a multi-unit auction, where first price auctions were the dominant design. Then when we moved to arbitrary smart contracts, it became clear that these transactions were not computationally indistinguishable. And so Ethereum models this as a one-dimensional problem where we essentially project the resource amounts for transactions onto a single resource numeraire. And now the block inclusion problem is a knapsack auction for which EIP-1559 is the dominant design. And now with blobs and dank sharding, we've moved to a multidimensional knapsack auction, as we've seen that one dimension is not sufficient to capture the demand. And the market design problem for this last column is substantially less clear than the former three. We are seeing markets that are popping up to clear certain types of this demand. For example, roll-up fee markets, shared sequencing, and prover markets. But what is becoming clear is that the general problem of matching supply and demand in this resource-intensive off-chain setting is something like a general two-sided marketplace, where on one side you have transactions that are demanding trusted computation, and on the other side you have nodes that are willing to execute these transactions, but perhaps face heterogeneous costs. And so the focus of this talk is about whether or not we can say anything about this general market design problem. So we consider a model where there is a set T of transactions that each demand computation, and there is a set of nodes that can each execute bundles of transactions. Each transaction comes with a valuation that expresses the transaction's willingness to pay, and each node faces some idiosyncratic cost for executing a given bundle of transactions. An allocation then specifies for each transaction which nodes are responsible for their execution. Multiple nodes could be responsible for execution if, for example, a transaction is parallelized or sharded across different nodes, or if they're running something like an MPC scheme. And we can even have other constraints on allocations. For example, we might not want two different nodes to be executing transactions that touch the same part of a global state. So in this model, we wrap all these constraints into a single validity constraint and require that the allocation lies within some predefined set of valid allocations V. So what does a fee mechanism do? Well, it elicits the transaction valuations and node costs, and it spits out a valid allocation along with payment rules that specify how much each transaction must pay, as well as how much every node should receive as payment. And ideally, these fee mechanisms satisfy desirable properties, for example, efficiency, budget balance, incentive compatibility, and collusion resistance. So in the first part of this talk, we asked the question, does a generalized version of 1559 work for this problem? And what does that look like? Well, in general, 1559, like mechanisms, work in two different steps. In the first step, a base fee is imposed. And the purpose of this base fee is to give transactions a posted price experience. Ideally, if the base fee is set correctly, then all elicitation of the transaction valuations is done through this base fee. And all transactions that don't meet the base fee are excluded from the block. In the second step, all transactions that survive the base fee are then allocated to the nodes. Prior work has focused primarily on the base fee setting problem, but the problem of allocation is challenging in its own right, not just computationally, but also in attaining economic efficiency. In the previous talk, my understanding is that the allocation was assumed to be optimal. However, if making the allocation optimal requires additional elicitation of transaction valuations, then in a sense, the base fee is a bit moot. It's kind of defeated the purpose of having this base fee in the first place. And so in the next few slides, I guess what I'll show is that this further elicitation of transaction valuations may actually be necessary under certain market instances. So we start with a simple single-dimensional EIP 1559 example, where we have a bunch of identical transactions, and we can fit k of them into a block. We have one transaction that's a high-value transaction with a valuation of 1/2, and the rest are low-value transactions with a valuation of 1/2k minus 1. In the optimal allocation, we include the high-value transaction along with k minus 1 of the low-value transactions to get a total welfare of 1. But if we set the base fee to just isolate out this high-value transaction, we'll get a welfare of just 1/2. And on the flip side, if we set the base fee to be low so that everything gets in, the allocation problem is no longer trivial. And without further elicitation of transaction valuations, we may miss that high-value transaction and only include the low-value transactions. As a result, we'll get welfare again that's roughly 1/2. And so all this is to say that in this example, no matter what we set the base fee to, we can guarantee at most 1/2 of optimal welfare. And this problem is exacerbated when we move to the multidimensional setting. And here we consider an example where there's again one high-value transaction and 3 low-value transactions in a 4-dimensional EIP 4844 type of setting. The high-value transaction utilizes all 4 resources, and each of the low-value transactions only utilize 2 of the resources. But because all the transactions utilize the 4th resource, and we have a resource limit of 1 for the 4th resource, we can only include 1 transaction in the block. The optimal allocation includes the high-value transaction to get optimal welfare of 1. However, if we set the base fees such that the high-value transaction can get included, we must inevitably also let in one of these low-value transactions. And without further elicitation of transaction valuations, we may include this low-value transaction instead of the high-value transaction, which would yield a welfare of 1/3. And in general, in the d-dimensional case, we can guarantee a welfare of at most 1/d minus 1. When we expand to a setting where there are multiple nodes, and these nodes can have heterogeneous unit costs over each dimension, we can actually even prove a stronger result. So here we show that suppose that there is some dimension where there are k transactions that have different non-zero values over some dimension. Then market instances exist such that welfare may be at most 1/k, even if we were to elicit transaction valuations. So what's the takeaway here? In the last talk, you heard that these markets were optimal. Why? But then I'm showing you some examples that are seemingly indicating the opposite of this. What's the catch? And the main catch is that allocation is a challenging problem. Even in the single-dimensional 1559 setting, welfare can be 1/2 of optimal without additional elicitation of transaction valuations. And this is exacerbated in the multidimensional setting, where welfare can be at most 1/d minus 1 of optimal without additional elicitation. Finally, in the general setting, we really need bespoke pricing. Each transaction needs to be priced separately. Heterogeneity over any fixed dimension can lead to bad welfare, even with further elicitation. So continuing off of that last takeaway, in the next part of this talk, I'll actually describe a mechanism which I call the broker mechanism that will try to actually satisfy good properties. In general, this problem of bespoke pricing is tough to do in protocol because learning bespoke fees can be very challenging due to the lack of data. So what's the idea behind this broker mechanism? It's essentially to have a market that operates similar to Uber, where we have a broker and that broker makes a proposal. That proposal specifies prices that the transactions should pay, as well as payments that should be made out to nodes. If all parties agree to the allocation and pricing, then it's enshrined and executed, and the broker gets to pocket the margin, which is the gap between the payments made by the transactions and the payments made to the nodes. So how does this mechanism do? It is incentive compatible because the transactions and nodes get a posted price experience. It's also budget balanced. But what happens if the broker is optimally strategizing? Well, we do maximize welfare. The sum of utilities of all parties is maximized, but all of that surplus is extracted by the broker. And this is a pretty undesirable property. So how can we modify this to allow that surplus to be distributed back to the transactions and nodes? Well, one idea is to add multiple brokers and have them each specify proposals, and they'll compete, where the proposal that maximizes surplus under illicit transaction valuations and costs will win, and that broker will be able to extract the margin on his proposal. So how does this mechanism do? Well, again, the argument for incentive compatibility is much more involved now, but assuming that brokers play in a non-degenerate equilibrium of their subgame, we do get a type of incentive compatibility guarantee. It's also budget balanced, and crucially, the main thing that we wanted to fix, it not only maximizes welfare, but also maximizes surplus. So that goes back to the users and transactions. That said, this mechanism is not collusion resistant for the reason that examples exist where no collusion resistant allocation may exist. So here's an example where there's two transactions and two nodes. The top transaction needs both nodes to execute. The bottom transaction only needs one. And the surplus maximizing allocation is to allocate the top transaction to both nodes. The issue is, no matter what pricing we set between the top transaction and the two nodes, a coalition involving the bottom transaction and one of the nodes will exist that'll want to deviate. Despite this, we do have a modification of our mechanism that gives a weaker collusion resistance guarantee. The main idea behind this modification is to allow brokers to defend their proposal against other brokers' proposals. This modification also has some other nice properties. For example, it allows brokers to specialize in certain parts of the matching instead of specifying the full matching. But all this is to say that the mechanism is still a work in progress. We're still working on resolving problems around credibility and dynamic matching. But a simplified version of this protocol will be coming into production with the ritual protocol. Thank you.